All right. Oh, it's not time. We'll wait for a second. Hey, can somebody give me a thumbs up or something to let me know that you can hear and see me?
You're good.
Yeah, okay, thank you. All right. All right, gang, let's get started here. So when we were last together, we were talking about Green's theorem. It's this kind of rather amazing theorem that links together 1- and 2-dimensional integrals in the plane. So I asked you to go ahead and try some of the examples from the homework and so on, or see the ones in the book. Are there any of those problems that you'd like to ask me about? Anything that seemed unclear? No? Everybody's good? All right. So what I'm going to do is I have slides ready today, and I'm just going to be able to talk about them. Oh, Yang Zhu, you have a question?
Yes, because when I read the book, it says that so Green's theorem is basically it creates a line theorem with a a line integral with a integral over a area, right?
Correct.
And also the line integral has an orientation in it, right?
Yes, that's true.
So we define the positive sign for the counterclockwise, right?
Yes, right. So to make the theorem match, to make the two integrals match, you have to be careful to use the integral. The line integral has to go around the surface counterclockwise.
So my question is that, like, if we change it to the to clockwise, then we need to flip the sign, right?
Mm-hmm.
On both sides, right? Okay. So yeah.
Right. I mean, it's a general theorem that says if you choose to parameterize a path backwards, then in a line integral, all that's going to happen is you will change the sign of the integral that you're computing. In fact, let me just emphasize this. Before we brought the vector fields in there, I had you guys compute 1-dimensional integrals over a curve. And the book is careful to call those path integrals, not line integrals. And for the path integral, orientation doesn't matter. There's no forwards and backwards on the path. You just take the whole path, you chop it up into pieces, you need to multiply the length of each piece times the value of the function. Same idea as every integral that we do. However, when you went to compute the line integrals, then the direction did matter because you were going to be always taking the dot product of this vector field that was given to you with the unit tangent vector that pointed in the direction of travel. So see, there's always two unit tangent vectors. And so when it comes to line integrals, you have to pick one of those two and say, I'm going to take the dot product of the force field with this unit vector, tangent vector, as opposed to the opposite one. I can't move my hands around. Well, if you choose the wrong one, I mean, the dot product of this vector with those two things, they're just negatives of each other. So the only price you would pay if you went in the wrong direction is an overall minus sign. But, you know, that would give you the wrong answer. So you do have to pay attention. And let me just say, because you have asked about the word clockwise and counterclockwise, I do have to be a little careful about that. On funny shaped regions, the terms clockwise and counterclockwise have to be taken with a grain of salt. So let me just show you a picture of that. There's one in the book too, but this is something that's worth discussing, because we do use this in the, well, Green's theorem and Stokes theorem that we're going to discuss today. So suppose that I ask you to integrate over this disk, and I give you some sort of a function, and it happens to be a combination of partial derivatives like this, and I say, please compute the integral of this over this disk. Okay, no problem. You know that you can write this using Green's theorem as a line integral. It'll be the line integral of the vector field P comma Q, dotted with ds, but you have to choose the appropriate orientation, and I told you to go counterclockwise. So you go across, I guess some people like to write this kind of an integral like that. You're going around the unit circle counterclockwise. Now, that is true even if you don't have a disk. So I could start to deform the disk and have you compute the line integrals over regions that look a little bit more like this. And still the same principle applies, that you're going to be going counterclockwise. The same principle applies if I deform it a little bit more, so that I'm kind of drawing the letter C now. And the curve called C is supposed to be the boundary of this. And yeah, I still do want you to go counterclockwise, but that makes sense at the top. By the time you travel along to this part of it, it feels more like you're going clockwise. And well, that's okay. In fact, you can deform this all the way to an extreme where the region that you're integrating over now looks like a very rugged letter C, and the Stokes theorem is still valid. It compares the double integral over the domain D to the line integral over the curve C, but that curve C has to be parameterized in, well, it's the counterclockwise direction here, but when you follow it along, you find yourself going right to left along that straight edge, and then clockwise over the inner circle, and then from left to right over the other straight edge. In fact, if I push those two edges together, if I continue to deform this set D, what you would end up with would be an annulus, a washer. Okay, they call them washers in Calc 2, I don't know why, anyway. I can ask you to compute an integral over the set D. That would be this, what I've called the right-hand side here in Green's theorem. It can be written as a line integral over the curve C that's on its boundary. Well, I guess an ordinary person wouldn't call the boundary of D a curve. It's actually the union of two curves. But it would be, in order to make this integral match Green's theorem, I have to parameterize the outer one clockwise, counterclockwise, and the inner one clockwise. So that's just this. It's just doing this exactly, where you will go from the outer edge, you'd stop at some point, walk inwards, take the remaining part of the inner edge, and then walk back the other way along the exact same line segment. So here we're coming to what I was saying a few minutes ago. When you compute your line integral on the left-hand side, if you choose to take the exact same path but walk it backwards, then your line integral will take the same exact value but negate it, turned into its negative. So those two extra pieces that I threw in there, they will cancel each other out. So all you will have left really will be the integral of the outer edge taken counterclockwise, and then you have to add in the integral of the along the inner edge, but this time taken clockwise. So there is a recipe that covers both of those, and I will be referring to this later today, so I might as well say it. What's true in both of those cases, if I take a perspective view on this, you can think of this annulus, this disk, as sitting inside the XY plane, inside three-dimensional space. I mean, that all of the Green's theorem has to do only with two-dimensional space. Sorry about the shading here. But of course, I can embed two-dimensional space into three-dimensional space. So now the annulus that you see here, it's just a section of the floor, and I want a person to be walking along the floor in such a way that their head points up along the positive z-axis, and they can choose to walk along the edge in either direction, but as they do so, I want their left hand, their left fingers, to be pointing to the inside of the surface. I'll put an L here for a left hand. You have a right hand that sticks outside, but imagine orienting yourself in such a way that your left hand points, you know, into the gray area, and the right hand points into the white area. If you're standing on this with your head up, then if you get yourself into this configuration and I say walk forward, then you would be moving counterclockwise here. But when you force yourself into the same configuration over here, so get your left hand to point to the inward, you know, to the shaded area. This is the shaded area. If your left hand points to the shaded area and your right hand points to the white area, now when I say walk forward, you'd walk this way, which would now be considered clockwise. So that's consistent with what I said over there. So the little person walking with their left hand kind of touching the surface as they go, they should be touching the shaded area, not the blank area. Their left hand should be touching the shaded area as they go, and then they should walk forward in that position. That's how you determine the proper orientation. And that's quite a mouthful, which is why we always say counterclockwise. But it's more accurate in a situation like this. It's more accurate than saying counterclockwise. There, did I kill your question? I think I threw about as many words as a person possibly could to answer that question.
Thanks, sir.
All right. So let's actually review the statement of Green's theorem, and I'll try to show you some reasons why you should care about it, and then I'm going to generalize it. I'll try to make it a little easier. So here's Green's theorem. Green's theorem says that a certain line integral will match a certain surface integral. I put dA here because I want you to think about chopping up a surface and you measure the area of the pieces and you multiply them by this number. So this is a surface integral. You recognize doing these. You would probably use Fubini's theorem to evaluate one of these things. Sorry, get the sheet. On the other side, you see a line integral, and well, it's the curve over which you're doing the integration here has to be the boundary of the region that I have on this side. And in particular, this will always be a closed curve. The boundary of a region in the plane is a curve that does not itself have a boundary. There's no endpoints to that curve. And then you have to integrate this funny looking thing that has both a dx and a dy in it. Please remember that that's just one of the many notations we used for the same process that we understood, I think, a little bit more the physics in other notations. So I do want you to feel comfortable with this notation, but you have alternative notations that you can use as well. What I would have you do to think about this in a more physical sense is to take the two functions p and q that are written there and use those as the components of a vector field on the plane. So at each point x comma y on the plane, p of x comma y and q of x comma y will be numbers. Those two numbers together give me a vector in the plane. And then you compute a line integral around the curve against this force field, against this vector field. So we have seen this notation of f dotted with ds. I should have said another notation that we have used asks you to take the integral in the path integral sense. You integrate over that set of points, and you chop it up into little bits. You multiply the length of each one of those little bits times the following scalar valued function. Scalar valued function. You take the dot product of your force field with your unit tangent vector. I think I was calling that a U before, U for unit, not U for tangent. So you guys know how this is computed. You have to begin by parameterizing the curve. And then all this is a function of t, and you get your, there's a fudge factor in there and all that stuff. Okay, so I want you to make sure you understand what the two sides of Green's theorem are saying. The one on the left-hand side has a variety of notations, but the computational technique is always beginning with parameterizing the curve in the direction shown. And on the right-hand side, well, that's just a surface integral and, I don't know, Fubini's theorem or whatever you want. Change of variable theorem if it helps you, I don't care. So, why should you care? Green's theorem has some very nice applications. It tells you some very cool things that are not immediately obvious. And I'll return to this one that we actually talked about long ago when we talked about certain kinds of vector fields as being conservative vector fields. That was a term that I don't know where it came from, but it does have a formal definition. It simply says that your vector field is the gradient of some scalar valued function. So for you science and engineering people out there, let me tell you what you will always be thinking of. The capital F is going to be, that vector field will stand for some kind of a force, and the little f will be the potential energy function associated with that force. If there is one. Not every force has a potential energy function, but precisely the circumstances where there is such a potential energy are those occasions where the force field is a gradient. And what happens in this case? Green's theorem says that if you were to integrate around a closed path, you'll get a zero. Well, physically, that's no great surprise. I mean, if I ask you how much net work do I have to do to, let's say, raise a payload off the surface of the Earth and then stay in orbit for a while and then descend to come back to where I started, well, no net work is done. I have to do some work to get up, but then I get work out by coming down. If I had a paddle wheel or something associated to my sinking rock or whatever I threw up into orbit, then I would be able to recover the energy. So no net work is done. And if you successfully made it through the potential energy discussion in your physics class, you would say, of course, no net work is done, because the amount of work done would be the potential energy function at the beginning minus, or at the end, minus the potential energy function at the beginning. But if you went on a closed loop, those two numbers are equal, you get nothing. So it's an easy consequence from physics, but it's also an observation that comes out of Green's theorem. And I can actually give you the proof. When you tell me that your force field, your vector field, is a gradient of this thing called little f, well, here's how you compute the gradient. It's just those two partial derivatives with respect to x and y. All right, so there's your p and your q. The right-hand side of Green's theorem says you're supposed to take the partial of the second component with respect to the first variable minus the partial of the first component with respect to the second variable. So here I go. I differentiate this guy with respect to x, and then this guy with respect to y, and I subtract. But of course you're going to get zero there, because we have a theorem about these mixed second-order partial derivatives. It doesn't matter whether you differentiate with respect first to y and then to x, or first with respect to x and then with respect to y. You'll get the same answer. So the difference is zero. So the thing you're integrating on the right-hand side of Green's theorem is a zero, and therefore the integral itself is a zero, and that's what I claimed. There's your theorem. It's done. Now, you might object that, you know what, I wouldn't bother integrating over a closed field if I knew I had a conservative vector field, because as the theorem says, you just are going to get zeros all the time. So maybe this theorem doesn't sound all that useful, but it's very useful, and I'm going to need this observation later today and I guess on Wednesday. You can use this theorem, or Green's theorem, to your advantage, even when somebody hands you a line integral that is not over a closed curve. So this is the corollary. The corollary is still going to apply only in the case where your vector field is conservative, if it's a gradient vector field, if there is a potential energy function floating around. But what the corollary says is, when someone asks you to compute a line integral across a curve C, not necessarily a closed curve, but if it's a closed curve that goes from a point A to a point B, You get exactly the same value for that line integral if you take the same vector field, but change the path to any other path that you like. So the amount of work that's needed to raise a payload from the surface of the Earth up to the space station does not depend on which path you use to get there. You could go straight up, or you could go kind of, I don't want to call it a diagonal, but you know, gradually getting extra altitude with each loop around the Earth. Doesn't matter what path you use. And the reason you know it doesn't is because you would compute the amount of work done by just subtracting the potential energy function. Or you could use Green's theorem, because watch this. If I give you two paths that connect A and B, points A and B, I should call that one C1. If I subtract the integral across curve C1 minus the integral across curve C2, the negative of the second line integral, this is the comment, we've already made this a couple of times today, the negative of that line integral is the same as integrating the exact same vector field across the exact same set of points, but traversing those points in the other direction. So where I write the negative of the right-hand side here, that can be thought of as actually adding in the line integral of f over the curve that goes from B to A on that set of points. And then when you add the integral that goes from A to B on curve C1, plus the integral that goes from B to A on curve C2, well then those two integrals together will just add up to the integral of, again, the very same integrand, but now you'll be integrating over the closed loop that takes you from A to B on this path, and then back from B to A on that path. So you can always change your path. You're not forced to choose the path that was given. And you guys want that, because I know a lot of you have trouble parameterizing your curves. Or maybe you can parameterize them, but then you get a hell of an integral that you don't feel like integrating. So this theorem will allow you to replace your path. Please don't overread this. This theorem comes with a condition. This only applies in the case where your force field is conservative. But in that case, the integral is what we call path independent. Not only does it not matter how you parameterize a given path, but it doesn't even matter what path you use. Now, this does feel like a very special situation, but I can generalize this even to any vector field. If you ask me to compute any line integral for any vector field across any curve that goes from any point to any other point, this is a completely general line integral here, then I have a recipe for how you can compute this in a way that might be more appealing to you. Why don't you just look at where the points A and B are and choose a different path that appeals to you more? Integrate the exact same vector field over that new curve. Now, I still want you to go from A to B. I've already said that if the vector field happens to be conservative, you'll get exactly the same answer in both cases. But even if the vector field is not conservative, I can tell you how to fix it. You won't, in general, get the same integrals. But what you will get is that this integral is equal to this one plus a correction factor, and here's your correction factor. According to Green's theorem, you have to add in the result of computing a surface integral now. The thing you're going to integrate will be the same dq dx minus dp dy that we've seen several times. And the region of integration will be the space between the two curves. So if you were given the curve C, or I should call it C1, then you just do as I did here in the picture. You draw C1 and C2 as the edges of a region. They both start at A and they end at B, but I really don't care anymore, because when you put the two of them together, you'll have a closed curve. And integrating over the interior of that region, integrating this thing over that interior will give you exactly the correction factor you need. And the reasoning is the same as the reasoning that I just did in the case of a conservative vector field, because if you take this left-hand side and you subtract the right-hand side, well, now that's going to give you the integral over C1 added to the integral over the curve C2 run backwards. Well, you put those two pieces together and you've exactly given me the boundary, the closed curve that's at the boundary of this set. So by Green's theorem, that line integral minus this line integral will be exactly equal to that surface integral. Okay, so that's Green's theorem, making your life easy for you. All right, so let me show you an example here, just so you can see how this plays out. So what I've indicated for you here is, first of all, I gave you a vector field. This one is not a conservative vector field, as we'll see in a few minutes. So I do not expect my line integrals to be independent of the path that I've chosen. So suppose somebody gives you this curve C1, and it consists of those two little bits. I have to go horizontally first and then vertically. How much work do I do? So, you know, what if it's, I don't know. Okay, anyway, here's the force field. I sketched it at one point. I'll let you go through the calculations. This one would be a little longer to the right. But you have values of this force field everywhere. And when you compute these, the line integral that you're supposed to compute, well, you'll be chopping this up into little bits, and you'll be multiplying the vector fields at these points times the unit tangent vector here. And then you'll have to stop and parameterize the curve, the second half of the curve C1 with, you know, you'll have a different parameterization, and you'll get a different tangent vector. Obviously, this one points north instead of east. Wow, that's a lot of work. So my proposal is, don't do it. Instead, you can integrate along the straight line path. Now, you're not going to get exactly the same answer, but Green's theorem tells us the correction factor we have to add in so that we can calculate what that line integral would have been. But the formula that I just gave you a few minutes ago says that the integral around the curve C1 will be the same as the integral along the curve C2 with this extra correction factor put in. And you can see I've shaded in the little triangle that is the region that's bounded by those two curves. And the integrand, of course, is always what it is in Green's theorem. You're differentiating the second component with respect to x, and you differentiate the first component with respect to y, and then subtract. So I'll still have to do a surface integral. A line integral. I won't be escaping that. There's no escaping that one if you have, unless you had a closed curve in the first place. But this one I can parameterize it all at once with a very simple parameterization, just t comma t. As t ranges over the interval from 0 to 1, I will start t equals 0. I'll start at 0, 0, and I will end at time 1 at the point 1, comma 1. So computing the line integral is now easy. My region of integration has been turned into this interval, and the function that I'm integrating is, well, I'm supposed to take the dot product of the vector field with a unit normal, a unit tangent vector, and then I have to do the stretch factor, blah, blah, blah. Well, we had that magic observation, that gift from nature that says, no, all you got to do is evaluate your vector field at each point that you pass through. So when I'm at the point t comma t, the vector field will be a 2t from this and a t squared from that. And I don't have to worry about unit tangent versus any other tangent. I don't have to have the fudge factor in here because those there were two references to the speed and they canceled out. So here is just the derivative of this function phi, my parameterization. So this part is phi prime at t. And when you take the dot product of that function of t, vector valued function of t, with this vector valued function of t, you have this scalar valued function of t. You have to integrate it as t goes from 0 to 1. In my head, I can find an antiderivative, which I evaluate at 1 and at 0. And so I get a number very easily. So that's this line integral. It's not the line integral I want, but it's a start. All I need to do is now to add in the correction factor. And the correction factor will be this surface integral. So here I've written in the partial of q with respect to x minus the partial of p with respect to y. The fact that I didn't just get a flat out 0 means that this is not a conservative vector field. The thing I was given in the first place is not a conservative vector field. But that's okay. I computed the q dx minus p dy, and I will now integrate this over this triangle. Since I had y on the outside and x on the inside, I got my limits of integration very easily. The y-coordinates go from 0 to 1. When the y-coordinate is fixed, you can see the x-coordinates go from that guy's x-coordinate to that guy's x-coordinate, which are y and 1 respectively. So there's Fubini's theorem at work. The inner integral turns out to be, well, the antiderivative is x squared minus x. And at the two endpoints, you get a 0 at that endpoint, and here's the other endpoint. And I computed the integral with respect to y, and I got some numbers. That's the value of the surface integral that makes the correction term in here. So this line integral that I chose to compute was 4/3. This surface integral adds a correction factor of 1/6, and that tells me that had I actually computed this line integral, I would get 4/3 plus 1/6, which I guess is 3/2. So there's my final answer. I never did parameterize it. I used Green's theorem to avoid that work. Oops, sorry, that's page. Yeah? So that's an application of Green's theorem. Now, I do have to stress that when you want to use this application, it's kind of important that the picture matches what I've been saying. I said I wanted to take the integral of the original curve, the integral around the original curve minus the integral over the new curve. That was supposed to be equal to all this kind of crap. And okay, well, taking the original line integral minus the other one means you first follow the curve C1 and then you take C2 going backwards. And I can then use Green's theorem as long as I really did go counterclockwise around the shaded region. If you didn't, you'll have to either put the line integrals on the other sides of the equation or just remember that you have just computed the negative of what you really wanted to compute if you wanted to use Green's theorem. So that amounts to using a minus sign in this spot. And that occurs very naturally if I had kept exactly the same vector field in the previous case, the same points A and B, and I really wanted to use that same parameterization C2 that I just talked about. That's fine, but in this case, going around the original curve, C1, and then taking C2 backwards, well, that goes around this triangle now, you'd be parameterizing, you'd be walking around the edge of this one clockwise. So that's backwards from the way it's supposed to be in Green's theorem. And that's why I replaced the plus sign with a minus sign here. Okay? So are you guys clear on why I had to change the sign there? I don't want you to have a sign error when you aren't paying attention. Okay. Fine. Now, the next thing that I want to do is to show you how I can change at least the notation for Green's theorem. So Green's theorem has this crappy stuff you've got to remember. I mean, this looks fine, it looks pretty, and we have alternative ways of writing out the line integral. But on the other side, on the surface integral, you got to remember, I will confess, I sometimes have trouble remembering, do I put the Q first or the P? Do I put the X first or the Y? I mean, I'm always tempted to start alphabetically with a P and have the downstairs numbers go reverse alphabetical, but it turns out, no, it's the, anyway. So, you know, you're differentiating the coefficient with respect to, the coefficient of the dx gets differentiated with respect to y, and the coefficient of the dy gets differentiated with respect to x, and it's all confusing, and I don't know, Okay, so here is another way to write this in a way that might appeal to you. I started with a vector field on the plane. So P and Q were functions of just x and y, and I spat out just two components, the x and y components of the vector field. If I simply attach a 0 at the end, now every combination of an x and a y will give me a vector in three-dimensional space, but since the third coordinate is a 0, that's still just making the vector be flat in the xy plane. Of course, even though only x and y are mentioned, you could now think of this as a function defined in three-dimensional space. If you have a point x, y, z, Well, just ignore the z coordinate. In other words, you take your point and you project it straight down to the xy plane, and just use the remaining x and y coordinates to compute those two numbers. And when you tack on a 0 at the end, now you have a vector in R3. So this simple artifice of putting a 0 at the end gives you a vector field in R3 when you used to have a vector field in R2. This is now a function that's defined from R3, and it spits out values in R3. As a vector field, it's now going to give you little arrows that point everywhere in three-dimensional space. With that 0 there, it's going to, the arrows in the, well, the arrows everywhere are just going to be pointing horizontally. They'll be always pointing parallel to the xy plane. So in terms of things like fluid flow, when I describe a vector field in three-dimensional space, you guys are used to me talking about winds blowing and water going downstream and so on. Those are fluid flows, and the vector field is somehow indicating the velocity vector at each point. With the presence of a 0 here, what that is telling you is you just have what's called a laminar flow. So what happens on each, what starts on one level ends on that level. Nobody goes up and down. They're just going, you know, in sheets. That's why the word laminar is used. And specifically, since P and Q are functions just of x and y, that means that when I try to draw the arrows at some higher point than the xy plane, I'll take my point in three-dimensional space, go straight down to the xy plane, figure out what arrow I would have drawn down there at the bottom, and just lift that arrow upwards. So it's as if I made a million copies of the little arrow picture that I would draw in the xy plane, copied them on separate sheets of clear paper, clear plastic, and then stack them all up. And so I just have all those arrows pointing in three-dimensional space, but at every height it's the same as the one that I had before. So as far as vector fields in R3 go, that's not all that interesting. But because it's a vector field in R3 now, I can compute the curl of that. Every vector field in R3 has a curl, which is yet another vector field defined on R3. And you may remember this notation that we use, the del cross F, that's supposed to be a mnemonic that helps you remember how to compute this thing, if you remember how to compute cross products, that is. I mean, you write out what the del operator is. It's the sequence of 3 partial derivative symbols. And the vector field F is also a vector. At each point, you get a vector. Of course, the third component is 0, but anyway, it's a vector. And when you compute the cross product of 2 vectors, you know you get another vector, and you have a recipe for how to write down the 3 components of that new vector. So the first component, for instance, you get by, down here, you'll get that by putting the second symbol from the first vector times the first symbol from the second vector. First, second, third. You put the second symbol from the first vector next to the third symbol from the second vector. So I've done that here. And then you change the roles of the first and the second vector. So you put the third symbol for the first vector next to the second symbol for the other vector. So this should say Q. I actually wrote that wrong. Oh, yeah, that one's okay. All right, I think I'm computing cross product correctly. Stop me if I'm doing this wrong. But anyway, the I component of the cross product of 2 vectors, you take the J components and multiply them by the K components in the 2 possible orders, and you subtract. Okay, I'll let you guys compute your cross products, which is to say, I'll let you remember how to compute the curl. All I really need out of this is to observe that this first component is a 0. That first partial derivative is 0 because you're differentiating a constant function. It's actually the 0 function. So that's a 0, and over here you get a 0 as well because P and Q are functions of just x's and y's. There's no z's in there, so that partial derivative is a 0. And so is the next one. So the curl actually comes out to be this vector that's got 2 zeros as 2 of its components. And the third component is precisely the thing that Green's theorem says we're supposed to integrate. So this gives you a kind of a notational convenience, if you like. When I ask you to write down Green's theorem, you should know that it says that a certain line integral is equal to a certain surface integral. And the line integral, there's nothing special about it except that you have to integrate over a closed curve. That's one thing that's special. And everything about it is supposed to be in R2. The vector field is supposed to be defined on R2. It gives you vectors that are in R2, and the curve is supposed to lie in R2. But anyway, as long as it's a closed curve, you can compute this line integral on one side of Green's theorem. And on the other side, you're supposed to compute the surface integral over that, the interior of that region. But the thing you're supposed to be integrating is exactly what I see here. And if you remember that I computed that as a curl, it's okay with me if you just say curl of f at this point, because curl of f, it's a vector, but the only interesting component of that vector is exactly the thing you're supposed to integrate. Now that's just between you and me because I'm being permissive here. Really, every mathematician would say, no, a curl is a vector, and you don't integrate, this is supposed to be integrating a scalar valued function. Chop up areas, multiply values of the function times the area of the piece. And that should be a number, not a vector. And well, you guys know what I mean. I want the number that's in the third component, which is what you would get if you took that vector, and you see I put a little arrow over the word curl, just to remind ourselves that this is a vector, another vector field. But you're taking the dot product of that with the vector 0, 0, 1. So that just will pick out the third component of this vector. So this is an alternative way to write out what Green's theorem says. And in fact, you might notice, this second vector that I took the dot product of, I just took that particular vector so that it would peel off this third component. But that's a unit vector. And it points straight up, which is to say it points perpendicular to this surface here. So I could write that vector, I could just give it a name like n, because it serves as a unit normal to the surface over which I am integrating. And at that point, you realize, hey, this right-hand side of Green's theorem, I was calling it a two-dimensional integral. I was even calling it a surface integral, but now you recognize it as a surface integral in the sense of what we talked about a week ago. Somebody hands you a vector field, the curl of f is another vector field, and they say, hey, would you please integrate the dot product of your vector field with the unit normal at each point, and you calculate the integral of that with respect to area over this surface. In other words, it's this kind of thing that we have indicated this notation before for surface integrals. Somebody writes down here some vector field. Pay no attention to all the letters that are in there. This is just some vector field in R3. Cover it so you won't see it. Some vector field in R3. And they put the dot and the boldface ds, and then they hand you a surface, and they want you to compute that integral. And of course, you know what you have to do to compute that. You know what it means. You're actually going to take this vector field that I'm hiding, and you have to take the dot product with the unit normal, and now you have a number at each point, and you do the chopping up and the multiplication of the areas times the values of that dot product. All right, that seems like I've made things more complicated than what Green's theorem originally said, because now I've told you that the line integral is equal to a surface integral, which I know nobody in the class really likes. You prefer to have just the two-dimensional integrals that you can compute with Fubini's theorem. But if you can get over your aversion to surface integrals, I would point out that everything that I just wrote down, although I wrote it down for vector fields and curves that lay in R2 in the first place, the symbolism all makes sense for any vector field over any closed curve, even if it's in three-dimensional space. The curl is defined, the idea of a surface integral is defined, so at least there is a hope that you can interpret Green's theorem even for surfaces that don't just lie flat. And you might wonder whether the theorem in this form is still true, and it is, and that's now called Stokes' theorem. So, by the way, that S is part of Mr. Stokes' name. He was Mr. Stokes, not Mr. Stoke. So what does it say? It says, if you give me any surface, I should say bounded surface in three-dimensional space. Bounded surface means you can put it all inside a big ball, a big sphere that holds it, a finite radius sphere. I don't want to have something that stretches away infinitely far. But you can think about the word bounded in this context as meaning that it has a boundary. And I'm going to call that boundary C because it'll be a curve. But I've mentioned before that I can use this partial derivative symbol also to stand for the boundary of a set. So I've used that notation when I was talking about the fundamental theorem of calculus. The boundary of an interval was just the two endpoints. In the fundamental theorem of calculus for line integrals, the boundary of a path was its two endpoints. All right, anyway, give me any bounded surface. Figure out what its boundary is. There's a little technicality in there I'm going to have to come to. And give me any vector field in three-dimensional space, any one at all. Then, if you proceed to integrate that vector field over this curve C, the boundary of the surface, and this is a line integral in the same sense that we've been talking about, everything the same except it's not in the plane anymore, it's in three-dimensional space. You got to parameterize the curve, you evaluate the vector field at each point on the curve, you take the dot product with your velocity vector, and that's what you integrate. Mr. Stokes tells us that that can be written as a surface integral, and now I mean a surface integral of the complicated type, where you take this vector field, not the original one, but the curl of that one. That's another vector field in three-dimensional space. And compute the dot product with its unit normal vector, the surface's unit normal vector. Then that dot product is a scalar, and I want you to compute that scalar integral. So this is the kind of thing which we had a new notation for. We wrote it as, well, as this. The dotted with, taking a dot and then the ds, with that capital S is usually in bold or it has an arrow or something. That's the notation that we use. It's kind of like the pdx plus qdy notation for line integrals. So you know how these things are computed. You have to begin by parameterizing the surface, and you evaluate the function, and then you have to take the dot product with the normal vector that you get. There's your t sub u cross t sub v thing, okay? So Stokes says that those two weird kinds of integrals will be equal. Now, I won't have time today to do examples. I'll do examples with you, but I do have to clarify one thing that's important. On a surface, we've discussed the fact that you get to choose at each point two possible normal vectors that are opposite each other. One goes up and one goes down, or one goes in and one goes out, or whatever. And there's nothing wrong mathematically with using either one, but probably only one of them makes sense to you in an application. So someone would give you the surface, and I guess they give you the vector field, but they would also indicate somehow which of the two normal vectors you want. Or maybe I should say, which of the two normal vectors they want. So then they want you to compute this surface integral. They've made it clear what they want on the right-hand side. On the left-hand side, there's still some ambiguity because it's not clear how to orient that curve on the boundary. And you can't say counterclockwise anymore, because I invite you guys to imagine two people standing next to each other. They're going to talk about a curve that they see in front of them, or between them, which is a hula hoop held vertically. And they want to parameterize that curve. If they both try to trace that out counterclockwise, this person would be tracing it this way, and the other person would be tracing it out that way, and I can't make my fingers do the opposite at the same time, but they would be opposite each other. So the piece of information I have to give you is which of the two orientations on the curve is going to match what you see on the right-hand side. And as it turns out, there's two possible orientations here. They will match the two possible choices of the unit normal vector on the other side. But to know which one you want, what you have to do is the same kind of thing as I was talking about before with that annulus. You have to draw your surface and draw the little normal vectors everywhere, including at the boundary. So these normal vectors should vary in a nice smooth way. That would mean they would be pointing upwards over here, on a surface that curves backwards like this, you understand that those stalagmites are turning into stalactites over there. That's okay. You have a consistent sense of where the arrows point. Your little person now needs to walk with their feet at the base of the arrow and their head at the tip of the arrow. So they need to be above the surface here and then walking on the ceiling there. And furthermore, before they start walking, they have to twist themselves around so that their left hand is scraping the inside of the surface. So I know my picture is kind of confusing here. I tried to draw a little bit better here. You put your feet on the surface, choose the side of the surface to put your head on so that your head is up the way the arrow points. And then you can still sort of look forward or backwards along this curve, choose the direction to look that would have your left hand touching the shaded surface and the right hand points out into nothingness. Once you get yourself into that position, then start walking forward, and that determines the parameterization, the direction in which you need to parameterize this curve C. Okay, so it's what's called the induced orientation on the curve. It's the orientation on the curve that matches the orientation that was given to you on the surface. So I invite you to think about this. If you start all over again, but you draw the opposite arrow on this surface, have little arrows. Can I draw something in red? Would you see it in red? If I drew the downward arrows everywhere, well, they turn into the upward arrows over here. If a person now tries to situate themselves so that they can mimic the arrows, then they're walking under the surface out here, and by the time they're walking over here, now they're on top of the surface. They still have to have their left hand dragging along the inside of the surface. So in this case, in this case, the person has to be facing that way so that their left hand, I gotta figure this out myself, yes. Well, it's easier for this person who's here at the top. For them to have their left hand dragging along the inside of the surface and their right hand pointing into nothingness, they've got to be walking that way now. And so that becomes the proper orientation on the curve that matches the red arrow for the normals. And you can see that it's opposite the way that I drew the blue arrows before. Okay, so either choice of the normals N is fine, but each one of them comes with its choice of which line interval you're supposed to do. All right, I just reached the end of my hour, so I got to stop here. Do you have any last minute questions about how I've set this up, how the statement of Stokes' theorem is supposed to be understood? All right, next time we'll start, on Wednesday we'll start with the calculations. We'll do some examples of these, of Stokes' theorem, and they will have the same side effects, the same corollaries and so on that we had for Green's theorem, only now it'll apply in three-dimensional space, so it'll be a lot cooler. When is the final exam? Somebody's asking me. I meant to ask the other class too. Hey, this came up on Piazza, and I realized I did not have a good answer. What I proposed on Piazza was this, that your two classes of 427L, I was going to have you take the same final, and I wanted it to match your regular exam time, but you guys have different exam times. So the way to make this work is, one group has their exam time on Wednesday, May 13th from 9 to noon, and the other has theirs on Saturday, the 16th of May from 7 p.m. to 10 p.m. So what I'm going to do is something similar to last time. There will be a quest component and a take-home, free response component, time windows and all that stuff. But the starting moment for the whole shebang will be at 9 a.m. on the 13th, which is when one group starts, and it'll end at 10 p.m. on the 16th, which is when the other group is supposed to end. So how does that sound to you guys? Do you have any feedback to that choice? Okay, if you have a problem with that, let me know. I can make adjustments for individuals, I suppose, or if there's a lot of people that have a problem, I'll change it for everybody. But That's probably the fairest way so that you can claim that I haven't really changed your exam time at all, and at the same time, I'm giving you a lot of time to finish the exam.
Can you please repeat the hours?
Yes, so the intention is it'll start on Wednesday, the 13th at 9 a.m., and it'll end on Saturday, the 16th at 10 p.m.
Got it, thank you.
Okay, so and no matter what your time zone, no matter what your schedule of your other exams, it's the same thing I've always been saying since they threw us out of the university was grades really, grades hardly matter this time, but I want you guys to feel like you've really been examined and you have a chance to work these topics. So the final is cumulative, but in particular, that means it's going to have all this stuff from chapter 8. All right, let me cut it off here and then maybe ask me more questions about that on Wednesday if you need to. All right, guys, I'll switch over to office hours now if you need help. Otherwise, I will see you on Wednesday.